Hello everyone, this is 𝐒𝐞𝐜𝐮𝐫𝐤𝐻𝐿. I'm currently serving as a visiting assistant professor at University of Cincinnati in USA. Today, I'm going to present our paper titled PEARL, a reinforcement learning based attack analysis approach for security and robustness assessment of smart home systems. Do you know the air inside our homes and offices can actually make us less productive or even dizzy? Who are the main culprits? The people and everyday appliances. They release heat and carbon dioxide, which slowly degrade the indoor air quality. To deal with this, the heating, ventilation, and air conditioning systems bring in fresh outdoor airs, which helps reduce carbon dioxide and keeps us breathing easy. But there is a catch. The fresh air is often too hot or too cold compared to our thermostat settings. On the other hand, the recirculated air or the return air has the perfect temperature but is packed with pollutants. That's why the best solution is an optimal mix of both. Modern systems go even further. They track how active we are. The more active we are, the more metabolic rate we have, the more heat and carbon dioxide we produce. For example, someone cooking works harder and he has more metabolic rate and he produces more heat and carbon dioxide compared to someone sleeping in the bedroom zone. If carbon dioxide rises too high, for example above 1200 parts per million, it can cause dizziness or fatigue. Smart HVAC system or demand control HVAC systems balances the fresh and recirculated air to keep us comfortable, healthy, and focused. Can your smart home control systems be attacked? In this work, we consider false data injection attack, where the attacker manipulates sensor readings to drive up the energy cost and cause financial harm. Here is how it works. We consider attackers parallelly perform passive sniffing by compromising Wi-Fi access points to silently monitor your smart home sensor measurements and actively tempering or altering your measurements by crafting maliciously the data packets. There are some demonstration of interesting attacks where smart home app assistants can be maliciously activated through inaudible voice commands. And those attacks can even be initiated by a malicious power socket and secretly activating your Google Home or Amazon Alexa to create a havoc. Are false data injection attacks just theory? These threats became reality starting in 2017 in smart home systems. Let's look at the timeline. In 2017, hackers exploited Heatmiser thermostat system to raise the home temperature dangerously. The next year, Google Nest Baby Monitor was hacked to deliver terrifying threats. In the year 2019, attackers compromised a Google Nest system and spiked the room temperature to a sweltering 89 degrees Fahrenheit. In the year 2020, Amazon doorbell was hacked to deliver racial slurs. In 2021, a hacker breached a water treatment plant in Florida, drastically increased the sodium hydroxide level to make the water poisonous. So those attacks are not hypothetical. These are documented attacks that compromise the security and the safety of smart homes and other critical infrastructures. In our security analysis, we examine multiple modern smart home defense components to create a realistic scenario to identify practical attack vectors. We consider a smart home system that uses activity recognition through a smartwatch, RFID sensor, or appliance sensor that leverages machine learning models. In a smart home, controls happens through voice commands and smartphone apps. We also consider a machine learning based anomaly detection model that learns the behavioral pattern of the occupants inside that home. For example, it learns the patterns like if an occupant enters into a zone at a certain time, how long he or she is expected to stay there. Any time outside that range is considered as an anomaly in our scenario. We call the controller perceived state as cyber state, which might mismatch the actual physical state of the occupants due to the attacks. Now that the background information is provided, here is the outline for the rest of the presentation. First, I'll discuss the problem statement and review relevant literature. Next, I'll present our attack model. Then I'll compare existing methodology with our proposed framework. Finally, I'll share the evaluation result using a real-world dataset. In this work, we model a smart home demand control HVAC system with an activity recognition model and a machine learning based anomaly detection model. We aim to devise an attack analysis framework capable of identifying stealthy false data injection attack vectors with variable attack attributes. The state-of-the-art work in this domain is our earlier framework named Shatter that used formal attack synthesis strategy to achieve this goal. The framework validated the identified attack vectors using a real-world prototype testbed. The literature addressing the similar problem scope can broadly categorized into two groups: rule or regulation-based analytics and machine learning-based analytics. However, these approaches cannot identify attack vectors targeting machine learning-based models. While formal verification tools like ReduPlex or Marabou exist for machine learning model verification, they remain unable to synthesize attacks. Adversarial machine learning tools can generate attacks, but they cannot guarantee that the identified attack vectors will comply with the defense tool requirements and maintain stealthiness during execution. Now let's talk about our attack model. Here are the control and attack assumptions. We consider that the sensors have no sensitivity issues and precision errors. We also consider the activity recognition model is accurate. All the actuators cannot be altered or activated similar to the smart appliances. For example, air supply or return vents or air supply or return fans cannot be directly controlled through smart devices like smartphones or voice-activated devices. Here we consider the controller and the communication link between the controller to the actuator is out of attack scope. We consider that attacker is aware of the surrounding weather patterns, smart home attributes, occupancy information of different zones, underlying control and defense mechanism. For the adversarial attribute, we considered that the attacker has accessibility to subset of the resources, if not all. Here the resources are the sensor measurements. The measurements could be indoor air quality measurement, it can be the occupancy measurement of the home, or even the status of different smart appliances. The attack goal is to maximize the energy consumption of the home and evade the machine learning based anomaly detection model, which looks for inconsistencies in the occupancy or indoor air quality measurement learned from occupants' behavioral pattern. Our attack vectors also need to evade the occupants. For example, if the attack vector turns on a washer in the kitchen while the occupant is cooking in the kitchen, will lose its attack stealthiness because occupant will figure out there is something wrong going on in his home. We also demonstrate the attack feasibility through a small testbed in our work through a Raspberry Pi based attacking device that runs Kali Linux OS and intercepts packets between Node MCU sensor nodes, each representing a zone in a home, and it uses a 𝐒𝐞𝐜 library to capture and modify the occupant data in that home. Let's now discuss about the state-of-the-art framework. In the previous framework named Shatter, we had taken all the control constraints that encoded the temperature control, ventilation control, and DC HVAC cost calculation constraints. We also added the attack constraints. These are the constraints that we discussed in the attack model. The most difficult part was to model the nonlinear machine learning based models. It is because all these constraints were later sent to a satisfiability modular theorem based solver, which cannot directly work with the nonlinear constraints. Hence, we converted all the nonlinear anomaly detection model constraints into a convex hull based linearized constraints. This problem can be viewed as a constraint satisfaction problem, and it is a NP-hard problem since it is a scheduling problem. In this work, we considered that the control period is 1 minute. Hence, throughout the day, there was total 1440 time slots. The complexity of this problem became 5 power of 1440 since there was total 5 zones. With all the constraints sent to the solver, finally we got an attack schedule that scheduled all the occupants into different zones, which is different than the real-time occupant information. But to launch an attack on the appliances, we had to tune that is scheduled based on the real-time occupant location information so that the attack becomes stealthy. The problem can be considered as a dynamic problem. However, since it is an NP-hard problem, to solve the issues, we had to divide the entire anomaly detection model into a smaller time windows, and then we found the attack vectors from those smaller time windows. We found total 4 research gaps from our previous work. First of all, the earlier work works based on an approximation linearized model, which loses a lot of significant details of the ADM, and many possible attacks are overlooked. When we started finding attack vectors using a reinforcement learning based approach using the actual anomaly detection model, which is a nonlinear model, we found another interesting problem. It is because we can see there are some flexible spaces around the actual data points. But now when we try to find out attack vector, sometimes there are some cases where taking an initial guess through the reinforcement learning based approach later found to be into a deadlock state. For example, if Alice is staying for 100 minutes in a particular zone, and if she entered at the zone at 1 p.m., that might be consistent with the anomaly detection model rules. But after 100 minutes, means at 2:40 p.m., she has to be scheduled to a different zone. But in this case, we can see that there is no zone where we can schedule Alice. Hence, it becomes a deadlock problem that we try to figure and solve using our proposed strategy. Another problem of Shatter was it used window-based optimization, which is mainly responsible behind the deadlock scenario. In our proposed work naming pernicious energy attack using reinforcement learning, or PEARL, we attempt to solve that problem. PEARL, unlike Shatter, can identify attack vectors in a specified time window. The key contribution of our proposed reinforcement learning based attack analytics, or PEARL, is that it can overcome the limitations of the Shatter framework, and it formulates the attack schedule identification as a Markov decision process. We consider a Q-learning based reinforcement learning approach where we encode each and every state as the occupant's zone, how much time he is staying at that zone, and when he entered to that zone. Hence, the overall state space becomes the number of possible time slots times the number of zones and the number of occupants in that home. From a particular state, a person can transition to any other zone. In this training process, we provide a positive reward if the occupant can be scheduled to a zone that can encounter higher energy consumption. To avoid the deadlocks, we provide a negative penalty to the deadlock states. During the training, we also tuned other hyperparameters for appropriate training procedure. One of the core contributions of PEARL framework is that it removes all the redundant states. The state reduction works in two phases. Before the training, it removes all the infeasible states. So almost more than 90% of the states gets removed through this process. Now during the model training, once a deadlock state is identified, all the preceding states are removed that do not have any other branch to transition to states associated with a zone different than the zone in that particular state. We evaluate our framework on some research questions. The evaluations are conducted on a real-world dataset named ARAS, which consists of two houses, each containing two occupants. The first research question is, what is the impact of the PEARL-generated attack vector? So PEARL can incur 3 times higher energy cost than the benign energy consumption, provided that the underlying anomaly detection model is density-based clustering model. So what is the framework's capability in extracting attack vectors from actual anomaly detection model? So PEARL can extract attack vectors from machine learning based anomaly detection models without linearizing the models. Unlike the previous approaches, the proposed framework can identify attack vectors from the actual anomaly detection models. For example, the attack vectors extracted from the DB-scan based ADM with full attacker's knowledge can incur a total cost of $810.11. In contrast, the linearized model experiences an energy cost of $738.11, which is more than 8% less than the actual anomaly detection model. So, what is the framework's capability for recovering from deadlock? If we take a look into Shatter, it encounters deadlock in all cases when the attacker has full ADM knowledge. In the case of partial ADM knowledge, deadlock occurs in most datasets except 𝐒𝐞𝐜𝐻𝐴01 dataset. In contrast, PEARL can always generate an attack schedule across all 1440 time slots. How to determine the convergence of the proposed framework's RL models? A key concern with reinforcement learning training is determining the stopping criteria or convergence point. Our experiments show that PEARL models convergence within 20 training episodes for different cases. While most attack vectors stabilize quickly, occasional fluctuation can occur as the algorithm explores better solution in the process. In conclusion, we proposed a novel attack analytics that can extract or identify attack vectors bypassing machine learning based nonlinear anomaly detection models. Our approach improves threat analysis by identifying critical vulnerabilities and potential attack impacts more effectively than the existing methods. Using optimized strategy, we reduced unnecessary states by 95% for a Q-learning based attack vector identifier. Our proposed framework identified attacks that could increase energy consumption more than 50% than the state-of-the-art framework. Thank you everyone for listening. Please send me an email if you have any questions.